Today I will discuss and explain the linear property of Fourier transform. Okay, and the properties which is defined as f1, yes, f of c1, yes, f1x plus c2, yes, f2x, yes, this is equal to c1 f of f1x, yes, plus c2 f of f2x, yes, this property. I have discussed this property, linear property of the Fourier transform. Okay, now where c1 and c2 are, yes, where c1 and c2 are, yes, constants. Okay, yes, clear? So on the first property I have proved this, and similarly we define the linear property of sine and cosine property. Okay, that is the next one property is second property is for the sines property, yes, c1 f1 x plus c2, yes, f2x, this is equal to c1 f sine of, yes, this is f1x plus c2 f of s sine of, that is f2x. Yes, clear? And similarly the third property we have proved here, which is cos property. Yes, that is f of c1 f1x, yes, plus c2 f2x, yes, this property. This is again is equal to c1 f of c f1x plus c2, yes, fc, that is cosine, yes, f2x, yes, yes, these are the linear property of Fourier transform. Okay, now we proved all the properties, yes, so first one we have proved, yes, yes, for the first property, yes, for the first property, yes, we have take the, for the first property we have take the LHS of this property, yes, so f of, yes, c1 f1x plus c2 f2x, yes, this is equal to, now here we are using the definition of the Fourier transform, which is equal to minus infinity to infinity e to the power ipx, yes, and the function which is this one, yes, which is c1 f1x plus c2 f2x, yes, this one dx, yes, so this can again be written as, yes, this can be written as c1 minus infinity to infinity e to the power ipx f1x dx plus c2, yes, minus infinity to infinity e to the power ipx f2x dx. Yes, and this can be written as, first one is Fourier transform of f1x and this is Fourier transform of f2x. So we can write here c1 Fourier transform of f1x and similarly c2 of f of f2x. Yes, clear? Similarly, we proved the second property. Yes, similarly we proved the second property. Yes, okay. From this property, we take the LHS, that is f of s, yes, which is c1 f1x plus c2 f2x. Yes. Here also we using the definition of the Fourier transform, yes, which is equal to here we use the definition of the Fourier transform for the sine series. Yes, okay. We know 0 to infinity. Yes, c1 f1x plus c2 f2x. Yes, and again here is sine px dx. Yes, this is the sine series. Yes, okay. So this can again be written as c1, yes, 0 to infinity f1 x sine px dx plus similarly c2, yes, 0 to infinity f2 x sine px. Yes, clear? Again, this can be written as sine of Fourier f of sine px, f of Fourier transform of the sine series and Fourier transform of the sine series, c1 of and c2 of. So this can be again written as c1 f of s, yes, f1x, yes, plus c2 f of s f2x, which is the right hand side. Yes, okay, here you see that this one. Similarly, we can prove for cos series. Yes, similarly we prove for cos series. Okay, the third property, yes, which is cos property. Yes, f of c, c1 of, here we also take the LHS. Yes, c1 f1x plus c2 f2x. Yes, this one. Here we again apply the definition of the cos series, cos transform. Okay, so then we get 0 to infinity c1 f1x plus c2 f2x, and here is again for cos series, so you write here is cos px dx. Is clear? Similarly, now again this can be written as c1 0 to infinity f1x cos px dx, yes, plus c2 0 to infinity f2x cos px dx. Yes, clear? And this again, according to definition, this is the cosine Fourier cosine transform. Okay, so this one is equal to c1 of fc f1x. Yes, clear? And similarly, this can be done as c2 of f of c f2x. Yes, clear. Okay. So in this way we have proved the linear property of the Fourier transform. Okay students, next video I have defined you the other properties. Okay, thank you.